So thank you, first of all, for here. It's very nice that you set up here. And it's wonderful to see such an initiative. And it's great. It's a real pleasure to be a part of it. So thanks for having me here. I wanted to share a few thoughts about in the context of the energy requirements for quantum computation. I wanted to share a few thoughts coming partly from my own background on the fundamental energy requirements that is required for computing, whether classical or quantum computing. We'll try to make the point that actually, we shouldn't forget completely the energy requirements that classical computing requires as well. So my own background, just for context, is that I come from quantum computing mostly. So my background is in quantum thermodynamics with including quantum computing and quantum information theory. So a lot of what I'll be saying will be kind of heavily based on, we'll have a heavy foot in that area. All right, so obviously computation is, I'm probably going to repeat a few things that have been said today, so I apologize for that. Computation is ever more important, because we use it every day and it requires a lot of energy, right? And we can ask, well, if we look at the laws of physics, what are the ultimate energy requirements that we need to run some computation? Do we have some fundamental limitations that are imposed from the laws of physics themselves, not just because we fail to engineer something correctly, but really because of the laws of physics? And at the same time, we know that we have quantum technologies that are being developed and that they offer some great promise for additional advantage in computation, but not only for computation, also things like quantum simulation or quantum sensing. And we might as well ask, well, what is really the ultimate energy requirement for running a quantum device, whatever this quantum device is meant to run in the end? So let me start in the first part of my talk by thinking about how can we formulate what the fundamental energy requirements for already even just classical computations are for a classical computer, right? So that a lot of energy is being spent on computing. That's something that is absolutely clear, that I'm sure has been said in other talks today as well. There's a significant proportion of the total energy production over the world that is used in communication and the computing and related information technologies. And for instance, data centers, they use something like 1% or 2% or like order of 1% of the total energy production. And of course, we'd expect this to become even worse with the advent of AI and the different tools that we want to use that require more computing. So it's clear that we should worry about how much energy our computing requires, and we should ask, well, what are the fundamental limits that we're hitting up against? Right, so we can ask ourselves, what does a computer need to do? Why does it actually need energy? Well, it needs to be able to store your information reliably in a way that it will not be destroyed by the noise that it's exposed to. It needs to do things like switching accurately in the state. If I compute something and I want to change the state of my computer to something new that I've computed based off of its current state, I need to be able to update the state of my computer and things like that. And now we're gonna so this is a plot that I found from that was pulled up by the CEO of AMD, and it shows like a trend of the energy efficiency of computers over the past decade or so. And the point is, all right, we're getting better and better at energy efficiency. Well, we're also using more and more energy, but that's another point that was made in the previous talk, right? But we're getting better and better at energy efficiency, but really, what are the fundamental limits that that is gonna limit the further progression of this energy efficiency? Right. Perhaps one of the first important fundamental limits is Landauer's principle, one of the also conceptually simplest ones. And that's that Landauer, back in the 60s, realized that if I have a computer that runs that computes some logical function, for instance, or the erasure of a single bit of information, well, if it runs something that is logically irreversible, then necessarily there is an associated amount of heat that is dissipated into the environment, and that creates some heat. That creates, that means this energy had to be brought in the form of work, and that causes energy. That's an energy cost. It's a thermodynamic energy cost. And one way of understanding why this is the case, why this has to be the case, this isn't just some poor implementation. It is necessarily the case. That's because the way Landauer thought of it is that you can imagine part of your computer that actually stores your bits. Let's call these the information-bearing degrees of freedom. If I store some information about it, I don't know, like some yes/no information about some important question, and then the rest of my computer might be the environment, like all of the atoms that comprise all of the whatever excitations that I have in the rest of my computer that might be in some junk state, and I don't know what type of state. That this is kind of my thermodynamic environment. If I want to perform some logical operation on the stored information that corresponds to erasing the bit back to something that's completely blank, well, this information, this yes/no bit that I have in here, had to go somewhere. And it typically, it means that it has to go to the environment. Now that means that I've reduced here the entropy of my information degrees of freedom. I've reduced the amount of information content of this system here. And that also means that I've increased here the information content of the environment. So I've increased the entropy of the environment. And the laws of thermodynamics tells us that increasing the increasing the entropy of the environment always amounts to some dissipated heat. So Landauer also studied a particular toy model here. We thought, well, to clarify things a bit, you can imagine that I have a bit that I've stored in one well of I have some potential, let's say, and I have a particle that tells me whether my bit is 0 or 1. If I put my particle here, the bit is 0, and if I put the particle here, the bit is going to be, I'm going to interpret that as the bit having the value 1. If I want to reset this particle to 0, well, if you stare at this, it's going to be clear you can't do that with reversible dynamics. If I applied any type of reversible dynamics to the system, well, I could just invert all of the. I have to be able to reach 2 different states at the end, because otherwise, if with reversible dynamics, it's just a contradiction to say that I would be able to end up in the same state at the end of my dynamics. So you need something like dissipation in the system that will force 2 different initial states to go to the same final state. Now, you can ask, all right, we need some fundamental thermodynamic cost to reset a bit. How much is that cost specifically? Let's say I have so this is where there was a toy model that was proposed actually quite a few decades before Landauer already. And this toy model is interesting because it really kind of illustrates the thermodynamic energetic value that one bit of information carries. You can imagine, it's a bit of a stretch, but you can imagine a gas that consists of a single particle. And if this gas occupies a box like this, some container with a certain volume, you can interpret the particle as being either on the left side or on the right side of the box, but you don't know where it is. It's with probability 1/2 either left or right. And if I'm in a situation like this and I want to reset this bit of information, this system to a definite state, say I want to make sure that the particle is on the right, what I can do is I can push with my piston, and you can calculate the amount of work, thermodynamic work that you need to run this process. And after a while, the particle is on the right side of the box. So I've performed the process that I wanted. I've reset my bit from an unknown state to a definite state. But I've had to perform some work because I had to push against this particle. And you can compute what this work is. And in this ideal reversible limit, you get that you have kT, this kBT. KT is Boltzmann's constant. T is the temperature of the environment with which you're working in. And log 2, because you have 2 states, essentially. This tells you that this is the amount of work that you need to reset a single bit to the L0 state. So basically, for every bit that you're erasing in your logically irreversible process, you will have some energy cost that's of the order of kT log 2. Now, this is kind of hand wavy. I just threw at you a single particle gas, which of course doesn't exist, and I haven't explained things in any precise way, but I'm going to claim that there are many different ways of formalizing and mathematically proving what Landauer's principle is, and how you necessarily need to involve some thermodynamic requirements, some thermodynamic cost in order to perform logically reversible computation. So you can ask, well, over the years, how much of a limitation is this? Is it something that we're hitting up against and that's a severe limitation now, or is it something that we're still far away from? And I found this very useful plot here by Professor Douglas Cole, who plotted different technologies as the year progresses. And now you can see, like, if you, and he also plotted here the lines that correspond to the Landauer limit in this plot. So if you're, the Landauer limit would be this one here, it's room temperature, and maybe 100 times the Landauer limit, which might be associated to some limit that where you need, where you account for the fact that your transistor needs to be able to switch in finite time and not just take arbitrarily long time. Well, you see that current technology is actually not getting very far away. It's not very far away from it. So right now we might be something like, 10 to the 2, 10 to the 4 away from the Landauer limit. And these numbers are also a little bit old, so you might know, I wasn't able to find more up-to-date information yesterday when I prepared this. You have a question?
Yeah, good afternoon. There's something I never understood with the argument is that, let's say I consider an AND gate computer.
Yeah.
So it's irreversible logically speaking, but in the computer in practice, what you have is that you have voltage at the inputs and voltage at the output.
Yeah.
And the input voltage are still here when you have the tensor. So there's the global state of the system. For me, what I don't understand is that it's not like we lost the input bits. So I don't, the thing is that I don't understand how, when we say that we reach the Landauer limit with electronics, it's for me to implicitly assume that when the output bits have the irreversible gate appear, we lost the input. But is it really how it works?
Yeah. You won't have the input, like you're at some point, like you don't have a history of all possible inputs gated or paths in your computer that are stored there in the cloud.
What I mean is that if you imagine I have an electronic circuit, usually it's like we put voltage on the input, we look at the third line, that's the output, but okay, so maybe the input or not, but I don't see how it's.
No, I think you consider the output also in your initial state space.
Yes.
So suppose you put voltage in the input and you get an output. Now both the off and on output will still get mapped to the same output. So you have two states which map to one state.
That's right, yeah. It's good answer. Good way to see.
I'm not sure to see what you mean. Like, because for me, I will see an AND gate of three big gate actually, because the input are still here, but I don't see which one. But okay, maybe we can discuss.
Yeah. It's always there's always a bit of an issue between applying, I'll come back to this later, between applying this type of arguments from Landauer's principle to some actual setting, because there's always you always have to carefully pick out what you need, which ones, what are your systems, what do you apply them to, what's the before, what's the after, what do you want to count as work, what do you want to count as heat, and that's always a bit of a tricky issue. That's something I'm going to come back to actually. It's an important part of the story. Yeah, but that's a good question. Okay, so like this is the important part from the classical side at this point. This is when people draw this type of diagrams, they kind of make some interpretation to try to come up with some fair comparison that, well, the Landauer limit should correspond approximately to the time. Like you should imagine the step where you want to apply something like a Landauer limit is the step where a transistor switches in a way that it lost the initial. It's no longer has a memory of the state it was before switching. Right. That's kind of, this is the type of argument that is used in this type of plot. Right. So we're still a few orders of magnitude away from the Landauer limit, but at some point we're going to get close to it, right? So that's kind of the story currently for classical computing. Now I want to ask, well, what happens? What changes if we start thinking about quantum technologies, which is of course the theme of this workshop? And it turns out that you have some interesting features in quantum technologies that you do not find in classical computing. The first is you have things like quantum coherence and entanglement. So it could take, for instance, two energy levels and prepare them in some coherent superposition of them, which is not at all the same thing as preparing one or the other at random. that would be a statistical mixture. This would be some quantum coherence that has interference effects if I take multiple states like this, right? We have things like thermodynamic work is you can prove that it's not observable. It's not something that I can go and measure my system and tell me and have my system tell me, oh yes, this is exactly the amount of work that you use in your process. You have to worry about things like, is there any resource cost of actually keeping time, control of setting, driving my system in the right way. And these are things that are, of course, very much related between one another. They're kind of related to this idea of quantum resource cost of coherence. And they make things hard in the quantum case because make things difficult to formalize the quantum case because it might be that, for instance, well, the energy that I use or the word that I use by gate it's not just that I can't measure it, I can't access it, it just is not defined. It's not defined in the same way as if I take a superposition and I ask, well, does it have 0 energy or 1 energy? No, the energy of this thing is just not defined. If I measure the energy, I'll get something that is random and that has no value that is predetermined before I actually measure it. So by going and measuring the amount of energy that you use in a gate, you would actually perturb the process. You would change the process. You would be doing something different. So that makes things a little bit different because you can't just go and say, well, this is the amount of energy of force that I use in my gate, but I don't have to go and measure it. Then you have kind of weird effects that kind of might make you puzzle. They're not necessarily major obstacles, but you can have situations in which, for instance, you can design some type of big states where you can extract a macroscopic amount of work or energy from a state without perturbed by changing the state in a way that's indistinguishable from its initial state. And it turns out you have some weird things like that. And so that makes things kind of a little bit more delicate to handle. So if you wanted to say, all right, now I want to understand the fundamental limits of my, or like I want to understand how much resources do I need to involve in order to run a computation, you have different approaches that you can invoke, right? And kind of you have different levels at which you might want to derive some fundamental limits or some resource estimate. So first you might say, well, I have a quantum computer. There's a built fridge, there's your control lines that go down there. I have some superconducting qubits. I have some, you take all of the pieces of it, you kind of analyze them separately. You put everything together, you model the energy cost of everything, you put all of that in a machine and get some very nice analysis of, what the resource cost estimates like Marco likes to do. And that will give you a realistic estimate for something like a quantum computer. Now, there's another level at which you might want to derive resource estimates. That might be, well, okay, what if I'm interested not just in the resource cost of running this particular superconducting qubit, this is a superconducting quantum computer, but I'm interested in something more something more general that would tell me, well, whatever scheme I could imagine, then I would only be able to do this or that. So there are kind of two levels at which one might be able to do that. One would be, for instance, to say, well, let's look at a low level and just abstract out all of the different components of the computer and just say, I have some Hamiltonian or some Lindblad, some dynamics. And I fix some structure, maybe I say, okay, I store my system in this state and I do these measurements. And then I kind of look at all possible things I can do within this protocol structure. And this typically is the approach that you'd use in some statistical mechanics model, where you might use fluctuation theorems and things like that to derive general statements about the work statistics of such protocols. So this works well. You have another approach, which is closer to my own background and my own research background, which is a more kind of abstract first principles approach. You say, well, I don't want to assume anything about the dynamics of the system itself. I want to fix some kind of general rules that I want to stick to. For instance, that if I have some dynamics that if my system undergoes some dynamics that doesn't cost any energy, well, then the dynamics should conserve, say, the thermal state, something like that, right? I want to make sure, like, there's going to be some sanity kind of checks, if you think of it that way, some kind of border, some baseline rules that I want to make sure that I follow. And then I'm going to ask, well, what is the fundamental limitations that are imposed just by those baseline rules that I want to impose, right? And typically, this type of approach will give you a guaranteed fundamental limits that are valid with a very broad range of assumptions because we made very
Sorry to interrupt, but right now we have no sound.
You could, what you can derive as fundamental limits for quantum thermodynamics and for computation in quantum thermodynamics. Right, so, before we do that, sorry, I forgot this. Just to give you an idea, a better idea of what I mean by these three categories, in the context of usual textbook thermodynamics, you can imagine this first approach being, well, let's just take a steam engine and analyze all the different components of the steam engine and say, okay, this is how much, this is how many miles my steam engine will be able to run, and how much time and all the characteristics you're interested in your steam engine. This might be something like, well, let's write down a Hamiltonian for a statistical mechanical gas, and then write down, understand, observables of my gas and understand what I can do with this gas. And this might be closer to something like the laws of the phenomenological laws of thermodynamics, the way we learn them in thermodynamics 101, the zeroth law, the first law, the second law, where you say, well, you don't really care about how the system evolves, but all you know is that there are kind of some global constraints that are obeyed by the evolution. So one thing that I find very interesting is that the kind of in the past 15 years or so, right, there's been a confluence of different ideas and approaches that have enabled some really new approaches in quantum thermodynamics. And these are the type of approaches that will allow us to to come up with new fundamental limits to what you can do with quantum technologies and the computation. So we already had ideas from the thermodynamics of computation. That's what I told about. That's what I said earlier. Of course, statistical mechanics is something that's been around for more than a century, right? It's very old as well. Probably the oldest of what's here. Then a very important new thing that appeared that kind of drove all of this new research is really the ability to start, the ability to be the possibility to start and control individual quantum atoms and electrons and systems in a way that are sufficiently accurate and precise and to be able to control these systems coherently, so that we could actually access the quantum features of these systems. And that allows us, and once you start doing that, you start violating one of the fundamental principles of thermodynamics, where you promise you're only going to touch macroscopic things of your system. In thermodynamics, the first thing you say is, well, you can control energy, temperature, pressure, and then you promise not to touch any of the microscopic details. Well, with quantum technologies, you can actually start modifying and touching and controlling individual microscopic degrees of freedom. So this motivates really new ideas for how do we define even quantum thermodynamics at the nanoscale. What is even work? What is heat? We have to make sure that we can define things consistently here to be able to say meaningful things about thermodynamics for quantum technologies. At the same time, for the type of approaches that we took, another important development was the modern approaches to information theory that were also fueled a lot by quantum cryptography. So that's something that's more of a technical parenthesis, but it's something that is relevant for the development of these approaches. So now let me give you an idea of the type of way I like to think about these fundamental resource costs in something that we might call like a resource theory of thermodynamics, or something that's kind of close to some type of resource theory. This isn't strictly speaking the traditional resource theory. So the way we like to think about it is to say, well, let's imagine that I have some evolution that I want to, like I have some computation that I want to perform. And let's imagine that I have some agent, me, nature, whoever, and this agent is allowed to do whatever they want, right? They can compose processes the way they want. We're just going to stick to a few baseline rules, right? First of all, each process, I'm going to attach some value to it. It might be, maybe it costs something that I will call work. Maybe it doesn't cost anything. Maybe it can extract something that I'll call work. I'm just going to assume there's kind of some number attached to each process. And the thing is that we don't want to directly define, oh, this is for a given process, this is the number that you have to attach to it, because I'd be worried about not defining work correctly. So what I'm going to do is I'm going to rather just set some baseline rules, and the rules are going to be things like this. I'm going to assume that for each system, there's some preferred state, which is going to be typically the equilibrium state of that system if you just let it evolve on its own, right? So there's something, I'm going to call it the thermal state, but it's just every system just has some state, some quantum state that it prefers to be in. So this is the thermal state. And then the baseline rule you might impose is to say that one of the processes that the agent is allowed to perform, if this process can be done at zero work cost, or if it can extract work, then one thing I am going to impose is that that it conserves the thermal state. And then there is, as a process, as a dynamical map, right? So the idea being that if I have some process that brought my thermal state to something else, and if we happen to be able to find some implementation of a process like that did not cost any work, you'd create perpetuum mobile, right? You'd be able to extract as much work as you want because you take your thermal state, apply this process for free to bring you far away from the thermal state, and then use this non-equilibrium resource to extract again work to bring you back to the thermal state, and you just extract work for free. Now, to avoid some type of logical triviality of the theory, we're going to say, okay, we're going to assume that this is a reasonable assumption to proceed and say that, well, if I can do something without any work cost, the process that does it better fixes the thermal state. Yeah.
So here, how exactly you are quantifying the work? I mean, from conventional thermodynamics, like we know, depending on the system, like it's heat, main pressure, or volume, exchange of that. But now we are talking quantum. So exactly.
The thing is, I haven't told you yet. I haven't told you yet how to quantify it, right? Because the point is, I don't know how to quantify it. So I'm just going to state some things that my quantification, some axioms, if you like, that my quantification must satisfy. One of these axioms is that if the process has a work that's equal to zero, or that's less than zero, that I can extract work, then the process has the thermal state as a fixed state. It cannot bring the thermal state anywhere else than the thermal state.
You're assuming it has only one preferred state?
Yes.
Okay.
Absolutely. Yeah, good question. Right. And then the way I'm going to kind of the thing that's going to give me the quantification of work is this other rule that I'm going to impose, is to give a meaningful notion of work. I'm going to say, well, if a process has this number W on it attached to it, if it has this work W attached to it, then I'm going to assume that I can implement it by applying, by looking at a bigger system where I include the system on which I want to act and also something else which has energy levels. And I can apply one big process. There exists one big process that does not cost any work, which does the thing that I want on the system. At the same time, maps this auxiliary system from an energy eigenstate E to an energy eigenstate E minus the amount of energy that I'm using. Basically, I'm saying I'm going to assume that whenever I have a process that costs a certain amount of work W, then I can implement it always by a transition from one energy eigenstate to another energy eigenstate of some auxiliary system to model the fact that I'm putting in energy into my system. All right, so like these three kind of axioms, if you like, they're sufficient to kind of build up some theory of, if you like, some resource theory of thermodynamics or some kind of resource theory type. It's not exactly the way people think of a resource theory, but you can show things like this. You can prove that if I have some process that acts on some input system and produces some output system, and the quantum picture is purified by some environment, well, you can prove that the minimum amount of work that this process requires is something that's given by the conditional entropy of the environment, conditional on the output of the computation. And this is times this KT log 2 that we recognize from Landauer's principle. And this is the idea that this you can think of as a generalization of Landauer's principle. It's you need to pay KT log 2 for each bit of information that you dump into the environment that is no longer recoverable for the output. Right? That's what this idea of E conditional, this entropy of E conditional on X is. And if you now use this formula just to analyze some gates that you might want to, or some simple computations that you might want to make. For instance, if I have an AND gate, well, this is a gate that sends 3 different states to a single state. So in the worst case here, I'm going to have to use an amount of work that's KT times log of 3, because I have now 3 different states that I'm mapping to a single output state. On the other hand, if I take a gate like a C0, then this is a perfectly reversible gate. And if you plug in this formula, you're going to see that this is a gate that's not costing you work in principle. Of course, this is an absolute lower bound, right? It's more like a Landauer's principle type bound. In any practical implementation, you would have to pay more work than this because of all of the details of implementations and all of the things that have been neglected, like making sure that all of your thermodynamic processes run in a thermodynamically reversible way and so on. So this is more in the direction of a fundamental limits. Now, one important thing is that Landauer's limit and in the same spirit, the thing that we derived, it really assumes that you can run your system, you can run your processes arbitrarily slow. You need to be thermodynamically reversible all along the way. And you remember from thermodynamics, a Carnot engine, for instance, it has the optimal efficiency, but it doesn't have any power. So if you wanted to actually run an engine with some finite power, you're going to have to use something that does not operate at the Carnot efficiency. You need to pay in some extra work to be able to get that finite rate of energy out. So you can ask the same thing about Landauer's principle. We have Landauer's principle for some type of finite rate of computation, finite rate of erasure. And you have different protocols that have been proposed for Landauer erasure at finite time. And there's a beautiful result that came out a year ago, or a couple of years ago, in the archive, that proved some type of general trade-off between the time required to reset your bit to do your cooling to the ground state. So there was this trade-off between the time, the amount of energy that you were willing to invest, or some notion of control complexity that you're willing to invest in order to do this resetting. And kind of in parallel, we had also some ideas and some results on understanding trade-offs between the amount of complexity now thought of as a computational thing, like a circuit complexity that you might have on a quantum computer, and the amount of work that you need to perform Landauer erasure. So I figured I'd just kind of venture into this last result here to give you a taste of what I have in mind there, very briefly. So remember, that's what we just said, right? Like we have Landauer's principle essentially tells us, or the type of framework that we defined essentially tells us, that different computational primitives have a different amount of fundamental thermodynamic cost, right? Yeah.
No, I'm just trying to get a mental model of what one means by control complexity. Circuit complexity is a picture that comes right out of the mind, at least. But like,
I forget exactly what notion they used in that paper.
Okay.
It's some measure of like, you need to apply one big unitary onto your system because it's more than a qubit they consider a general system. You need to apply unitary, and then it is somehow a minimum number of things in how you need to decompose this unitary in terms of some elementary thermal operations. Right? They have some model of elementary things that you can do. It's a different model than what I presented to you, but it's kind of similar in spirit. And you decompose this big unitary into smaller chunks, and you kind of ask how many of these chunks you need. That, if I remember correctly.
yeah, okay.
So remember, if I want to reset a single qubit to the 0 state, this costs 1 unit of work. I just abbreviated KT log 2 by 1 unit, so it's kind of 1 bit. If I have a unitary, this is something that's completely reversible, doesn't cost anything in principle. And well, we can also look at something that's with the reverse of erasure. If I start with a pure state, and I know exactly what that state is, I can extract some work, some KT log 2 work by preparing the maximally mixed state, right? So remember, let's imagine, let's just work with a simple model where we have these operations here that we're allowed to do. Imagine that I have a pure state, I have a memory register in my quantum computer, it's in a pure state, and I want to reset it to the all-zero state. Now remember, I told you that unitaries, they don't have any fundamental work cost, right? I can just apply a unitary, and there's always some unitary that will map a given pure state to the all-zero states. I have 2 pure states, there's always some unitary that's going to map one to the other. And so you can say, very well, there's a way of resetting this quantum memory from the pure state to the 0 state without expending any work. There's a bit of an issue, though, is imagine that this state is actually very complex. Now, what I mean by that is, imagine that the state was actually something that you had to run a very long circuit in order to prepare, and that no shorter circuit would be able to prepare that state. Well, if you wanted to undo this, if you wanted to map the state psi back to the all-zero state, you would have to undo that whole circuit. You would have to run that entire circuit backwards, and you'd have to run some unitary that would have a very high circuit complexity, meaning that you need a large number of gates and therefore a large amount of time to reset your system back to the all-zero state. Now, there's something else you can do. This is a little kind of, that might save you some time or some complexity. That's if you just forget about this, the fact that this state is a pure state, and just go and brutally reset each bit one by using our, you remember on the last slide I said you could take a qubit in any state, reset it to the 0 state and pay KT log 2 work for that qubit, right? Let's just forget this is a pure state. We can even thermalize it if we want and make it turn into a maximally mixed state, and then pay KT log 2 for each work for each qubit, and then we're in the 0 state. We didn't have to run any long circuit. Of course, the cost is that we had to pay some work, right? There was some work cost associated with this process here. So this points to some kind of general work complexity trade-off. Some general trade-off between the work cost that you need to reset a state to 0 and the complexity cost that you need to reset the state to 0. So kind of this is one of the main motivations for the work that we did. We basically investigated the general case where we said, well, let's imagine I have some arbitrary state rho, and I am allowed to run some circuit with a certain number of gates. And then at the end of the circuit, I want to make sure that some of my qubits are already in the 0 state, and whatever's not in the 0 state, I need to reset manually by applying by KT log 2 work for each qubit here. Right. This is kind of the general setup of the problem that we looked at, and then we kind of showed that the optimal amount of work that you need to reset your state in this model here is given by some type of entropy measure that we defined. It's kind of some, I'm not sure the definition will be very enlightening. It's a generalization of an entropy measure that it was already known from one-shot information theory. The intuition I wanted to give you about this entropy measure is that it's a function of the state that kind of depends on like the number of gates that I'm allowed to put in here, but the number of gates that I'm allowed to put in here, I want to interpret that as kind of your ability to measure things, like what are you allowed to measure on your system. And so basically the point is that this entropy measure somehow quantifies how mixed the system looks if I'm only allowed to measure it up to a certain complexity of observables. So for instance, if I'm not allowed to measure, if I'm only allowed to measure things that are very simple, I could have a state that looks like it has lots of randomness, but in fact this randomness is just because I can't measure the right things to make it look like it's not random. And as I increase the complexity scale, I actually think I have some animation here, right? So like maybe if I'm here, that means that the state actually just looks random. It's not as random as it looks, but it just looks random because I'm not measuring it with the right observables. I'm not allowed to because the right observables would be too complex. And as I increase my complexity, my ability to measure complex things, at some point I'm going to realize that, oh, actually the state is more pure than I thought. So this entropy is kind of what quantifies that, and that in turn tells you here on this previous slide, it tells you again how much work you need with this type of protocol to reset a quantum state rho if you're limited in the number of gates that you're allowed to apply in the erasure protocol. So this was just kind of give you an idea again that we can start playing around with different ideas, with the different notions of fundamental limits for what you can do quantum mechanically, and like what type of processes, in particular erasure, you can do on a quantum computer. And so some of the interesting things here, for instance, is that you can bring in the notion of quantum complexity into thermodynamics. This has the advantage of being able to tell you something about, it's a way kind of restricting the amount of time that the process is allowed to take in the process that you're studying, right? And like it's a way, by saying the process must contain at most R gates, it's a way of saying this process is not allowed to take an amount of time that's longer than essentially something of order R. And one of the reasons that motivating this work as well is that complexity is something that's gaining additional attention throughout many-body physics, black holes, and chaotic systems. You have a question?
Yeah, it's just so okay, I understand the trade-off between the complexity and the work you spend. But my question is that the complexity you will have will also depend on the gate set you choose.
That's right. Yeah.
Could it be that it's a very naive question, but if it's like, could it be that you restrict to single and 2 qubit gates, you do not allow unitary, but that for one gate set of single and 2 qubit gates, you have exponential complexity, but for another one, it's polynomial, for instance?
No, yeah, that's a great question. I didn't tell you that. That's a great question, but the point is, one of the great results from kind of quantum computation is that gate sets, as long as they're universal, they're kind of equivalent. So you can usually simulate one with the other. That's the Solovay-Kitaev theorem. Right? You can, if I take one universal gate set and I want to actually, and I have a circuit that's expressed in a different universal gate set, I can always map one to the other with an overhead that's scales like the approximation, like one log one over epsilon or some square, I forget, and then some polynomial in the local dimension of your gates.
But if I remember correctly, like this was to approximate unitaries on 1 qubit.
On 2 qubits, for instance, yeah.
This universality, but like
That's
what
right.
is the allowed like interaction between many qubits in one circuit, and another one we don't allow that.
Oh, you can have large
Like, I thought that's
complexity.
what he was asking, right?
So what I was asking is more because if I know that if you allow interaction between all your qubits, then you do it in one step, basically.
Yeah, exactly.
But it was more like you have, let's say you force yourself to have single and 2 qubit gates, and you have two gate set that approximate well universal computation. Will it be possible that for one you need exponentially many gates, and for the other a polynomial number? The answer is no.
Well, if both gate sets are a few qubits,
Are restricted to the same number of qubits, right? Yeah.
that's how I understood the question. But you're right, if one of the gate sets is allowed to apply a unitary on all the qubits at once,
Then it would.
you can have vastly different computational power. That's right. Yeah, absolutely. So, like taking a step back, I thought one of the interesting points of this type of analysis is to say that, well, Landauer's principle actually it was really useful in the past to really understand the role of information in thermodynamics. Well, it turns out it's actually something that you can also use to try to get a bit more clarity on how complexity could appear to thermodynamics as well. Right, and complexity, of course, is related to all of the quantum computation technologies that we're developing nowadays. So now we wanted to turn more back to the theme of this workshop of, we have quantum technologies that are developing. We're developing for a good reason. We believe that they bring some interesting advantages. What can we say about their energy use, and what can we expect in the future? So first of all, in a certain sense, quantum thermodynamics itself, there was at some point in the past, some hope that by doing things quantumly, we'd be able to have a huge energy advantage or a huge thermodynamic advantage, or that we'd be able to do this or that better with quantum mechanics rather than with the boring classical mechanics. It turned out to be, well, either we hadn't had a good idea yet, but we haven't had the type of breakthrough that we might have expected earlier 10 years ago. So in a certain sense, so we do have features that are not there classically. You can have things like entangled heat baths that are not actually heat baths, that are entangled, and then you have heat flowing in very weird patterns. You can have things like that. But really, you have interesting phenomena, but no real advantage that you can pin down and say, oh, clearly, if I run this with the laws of quantum mechanics, you get something that's much more powerful than if I ran something similar classically. And this is very much in contrast to what we think about quantum computing or quantum sensing, where really clearly, by exploiting the laws of quantum mechanics, you get Heisenberg scale instead of a standard quantum limit, or you get increased sensing sensitivity, or you do believe that we have algorithms to solve problems that you wouldn't be able to do classically, or you believe you're not able to do classically. So now, so you can ask, all right, so we don't have any advantage necessarily. It's not clear whether we can get any advantage thermodynamically for thermodynamic tasks, but we do believe that we have some advantage for quantum computational tasks. So you can ask, all right, what can we say about the energy requirements of running quantum computation in terms of this Landauer mindset, right? So the first question you want to ask is the type, well, can we build something like a quantum computer that is going to be able to exploit an advantage like what quantum computing offers without having to pay a huge energy price for it, without having to, what is the energy price that we're going to have to pay for it? And I guess that's one of the aims of this quantum energy initiative, and it's a fascinating question. So some things that we can already say by thinking about kind of how Landauer might put in, and I think this is an area that we haven't really thought through yet as a community strongly yet. So I think it's these are very interesting questions. So first thing is that, if I have a quantum computer running a unitary circuit, well, unitary gates, they're reversible. So the unitary gates that are reversible. So in principle, as we've seen, they do not require any work in principle up to all of the implementation imperfections, right? But on the other hand, there are other models of computation that are definitely not unitary, right? If I do something like a measurement-based form computation, then I'm constantly doing measurements, I'm constantly getting outcomes that might, have some randomness in them. And these random outcomes, if I'm not careful about how I reset the registers that contain these measurement outcomes, we're going to expect that this can generate some Landauer type work cost. On the other hand, if I run something like a unitary circuit, I'm going to have to run that on qubits that are logical, so that there are error corrected. And in error correction, I'm also going to have measurements that I need to perform every cycle, where that are going to tell me maybe where my errors are in my physical qubits. And these also generate these outcomes that tell me where the errors are, and these outcomes will be stored on memory, on some memory register that will need to be reset according to Landauer's principle. So this will also give me some fundamental work cost. So we can already identify some areas where you can imagine some Landauer limits coming out, even if your circuit you want to run is entirely unitary and in principle completely reversible. So one thing I do find interesting is that the basic computational modeling which we think of quantum computing, that's in terms of unitary gates. And well, you have measurements, but you can always kind of defer your measurements at the end. But really kind of the fundamental building blocks you think of are the unitary gates. And that's kind of in pretty strong contrast with the picture in classical computing, where the elementary blocks that you have in classical computing are most of the time completely not reversible. They're assigning a value to a variable, adding things together, you're not going to multiply, most of the elements really do not, most of the building block operations that you use in a processor are not going to worry about being reversible. They're typically going to lose input information. So this is an interesting this is an interesting difference already in the basic computational model that we have, both in the quantum and the classical case. And I want to mention at this point that some theoretical computer scientists, they've proposed, well, we're going to reach this Landauer limit, and then we don't really know what we want to do after that. Some people have proposed that we should think about building computers that operate according to the principles of reversible computation. It turns out Bennett showed in some seminal results that if you have a computation algorithm, a classical algorithm, I can always turn it into a reversible algorithm without having to redesign the algorithm entirely. All I have to do basically is keep information about my inputs and then kind of cleverly put them in a way, like reverse parts of my computation in a clever way, so that I'm not left with the entire chunk of all of the inputs at the end. But I can always do my computation, turns out, reversibly. So in a certain sense, quantum computing may have the advantage of not having to kind of go through this step of, oh, we set up a computational model that's not reversible, but then we might hit the Landauer limit, so let's try to find one that's reversible instead. Quantum computing might have this advantage that we won't go through this additional step. On the other hand, quantum computing has this interesting feature that because it operates with these measurements, those measurements are things that you cannot undo, right? And essentially, the way Bennett showed that any computation can be made reversible, there's a fundamental primitive you need there, which is to copy information. And of course, quantum mechanically, you're not allowed to clone information. So that means if you have a quantum algorithm and in there you have some measurements, you typically will not be able to make it into a reversible computation. So there are some interesting differences there. So now looking ahead, I feel it's important to emphasize that we have good reasons to believe that we're going to get advantages for computation, for sensing, for quantum simulation. We also, I feel it's important still to remind ourselves we still do not know clearly exactly what the applications for quantum computing are going to be. We don't know what problems it is that they're going to be able to solve much better in classical computers. On the other hand, we do know that meanwhile, the power consumption of classical computers is still increasing, and that's very much worrying as well. And there are a few things that I think might be worth keeping our eyes open on, which is that quantum technologies, they might, of course, bring us a quantum computer. They might also bring us better ways of doing classical computing. Right? This is something that they might very much be able to do as well. Then there's a lot of unknowns still, and what and how the quantum computer would actually look like. Of course, we have proposals, but they still have lots of room to evolve. We don't even know what platform is going to be best, right? We have neutral atoms that recently had incredible breakthroughs for our correction, but we have superconducting qubits that show a huge amount of promise as well. We really do not know yet what the best platforms are going to be. And in any case, we talk about quantum computing a lot, of course, but quantum computers need classical computers, right? Because you can't operate a quantum computer if you don't run in parallel to it the decoder that will tell it how to correct the errors that are in the qubits, for instance. So even if you have a quantum computer with the components that operate at very little energy cost, if you need a very powerful classical computer that has a high energy cost next to it, maybe you haven't actually gained anything energetically. So yeah, I think there are some fundamental, and so the idea of what are the fundamental limitations for the energy requirements for computing, especially in the context of quantum technologies. I think these are some absolutely interesting, fascinating questions that deserve to be looked into even more. And yeah, thanks for your attention, and thanks for, again, for the opportunity to speak here.
So if I understand your talk very well, so if I want to do something useful with a quantum computer, I will have to measure and have to pay energy for the cost. There's only so much I can do with unit delegates, and without measuring, I can't really get useful information out of it.
I think the algorithm involves using the results of measurements. We need to spend energy, right? But just measuring is not a problem.
So yeah, the issue is going to be, right, so like the issue of, I didn't mention measurements earlier because measurements can be very confusing in terms of analyzing the work costs. Typically, measuring is kind of, you can think of it as a change of observer or rather copying information, right? Just, I find it much easier to think of measurements as just you're copying information somewhere else, right? Yeah. So instead of, instead of saying I measured here and I learned some value, I collapsed into value, I find it more convenient to think for the analysis of the work cost that I'm copying this information into some other memory register that might be part of my brain, the measurement apparatus or whatever. Right. So the copy part won't necessarily cost work if the initial state of your memory register in which you're copying is already pure, known state. What might cost work is afterwards if you want to reset that state to be able to measure something else later. Right. That's typically one way you can analyze the work cost of a measurement. So, but then the other thing I glossed over is that if you do measurements, what you mentioned, right? If you do measurement and then feedback again, or you do measurement and you want to reset a measurement outcome, or you say you want to do measurement, you do some feedback and then you reset the measurement outcome. Of course, because you use the value of the measurement, you can't just say, well, let's just undo my measurement, undo my copying, and kind of not worry about it because, well, you use that value, you can't undo the thing you used that value for. So typically but there still might be ways of doing that by using less work, as long as the information that you obtain with the measurement is still somewhere in your system. You can kind of conditionally on the thing in the system, do some type of C0, flipping your outcome register, and that is again a reversible operation that you could in principle do without any work costs. So depending on the situation, you might get away without any work costs, even though in principle, when you have situations that involve measurements, typically they're associated with some work cost because you need to reset the memory register.
My question was going somewhere else.
Sorry.
But this was helpful in the sense that, okay, now that this context, so if I'm going to use them in an error correction context, for instance, I'm going to use the measurement outcome somewhere, so I'm going to be paying some cost. So can I make this statement that, okay, if I want to do this in a faster manner, I'm going to pay more cost. So if I want to extract more measurements very fast, then I'm going to pay more cost and extend that to say, okay, so can I make some sort of statements that, okay, one kind of platform takes measurement times that are very fast versus sometimes very slow. Can I extend it to make some statement like, okay, this platform is going to cost much less energy than this, or if I'm going to speed up the slower platform, I'm going to have to put in some sort of energy to speed it up.
Yeah, that's a great question, right? And this is the type of question that you want to be able to answer. You're gonna navigate. It's gonna be delicate between navigating these different. Maybe the best picture would be these these different kind of approaches here, right? You're somewhere between like the Landauer type limits, I would see them as kind of here, right? But there you don't really have a notion of time necessarily, right? Or you can try to bring in some notion of time as complexity, but then you're kind of making some assumptions on like the gate set that you're going to use or some kind of details of your system. So it sounds like if you're talking about measuring faster or the slower rate, you need to do some type of finite time Landauer erasure. You're more in this type of framework here, right? So as long as you're okay with kind of deriving results, so my point is you won't be able to just use our result for that, for instance, right? You're going to have to derive something that's more ad hoc, it's more specific to that particular setting. But yeah, if you
at this point, like I don't really care about the gates, and I'm just like, okay, can I make my measurement? What do I need to make my?
In principle, the faster you want to do a process, the more work it's going to cost. That's kind of broad. The push sign.
Also, if I understand correctly, like all the quantities that you have used here, like your work and energy are all just self-defined quantities with no real relation to actual work and energy.
It's defined here, right? I've assumed that you have some energy levels in my auxiliary system. This is what defines.
Okay, okay. Nice. Oh, and I had a question here as well, this exact statement, right?
Yeah.
So, you say it has an energy level that transitions from E to E minus W?
Yeah.
Does it have to be one? Can't I like separate W over multiple energy levels and then?
Yeah, it's a great question. Yes, and the answer is like, this is the simplest version you can imagine. It's equivalent to many other things. It's equivalent to what you're describing, to have many different energy levels
and
in
just
position.
Group it into one.
So what do you mean by
like consider all of these many systems as one system, but like that doesn't make sense usually,
well,
because
you can do it in many ways, in many different ways. Like like the reason that I just picked this simple model is that even though it's specific, it's that you can pick many different models and it's going to be equivalent. And you can pick a completely different model that doesn't even mention energy. You can say, I'm going to look at a long kind of array of qubits, and the number of these qubits are maximally mixed and the rest are pure. And then the kind of, I'll define kind of how much energy or like how much work I've used by basically a difference in the number of qubits that are pure versus maximally mixed. And it's kind of, it works by a nice principle. But you can show that this model is equivalent to this one here within these rules. So I'm not sure I caught the one you had in mind, but it sounded also like something that would be
yeah. Like, so what I was like, you said one energy level, but you could separate that across multiple. Like, I'm considering energy levels as eigenstates here.
Yeah.
So, like, there could be changes in multiple eigenvalues.
Oh yeah, exactly. No, absolutely. This system could be like many spins, and then change exactly 2 levels of the main body spin. Absolutely.
There are more questions or no? Thank you so much again.